Chapter 4, Equilibrium. So for this chapter, there's going to be a whole bunch of problems like this where we have a structure that has some applied forces to it. It's pinned in place. Maybe there's cables or pin supports or roller supports. And we'll be given enough information that we can walk around and figure out the other forces acting in the system. And it's called statics because the forces in this case are not equal to MA. The forces add to zero. So if we have the same amount of force pulling horizontally on two different points and the same forces vertically happening through the system, and it's not rotating, walking through these static equilibrium problems will help us to find the internal forces to the system. So sometimes we're not even worried about the thing moving. We want to know how heavy duty of a cable do we need, or how much force is pushing on this little bolt. Think through statics, think through how it's going to fail. So if that tension in the cable is tightened too much, what would happen if the tension was pulling too much, right? So the whole thing would rotate. Or maybe the tension in the cable wasn't enough. Maybe the tension breaks. In that case, the whole thing would fail a different way. So think through how it's going to fail, and that will help you draw your forces for your free body diagram correctly. So free body diagram, what you're doing is you're taking one section of your system. I guess that's what free body means. So for this system, we have, the ground and the cable, and there's birds flying around, and we're not going to analyze the entire thing. You carve it into pieces. So I'm going to carve out just this piece of it, and we're going to draw all the forces acting on just this piece. Some of these forces will be given. So the problem statement tells us the force that's acting at point D. Usually these guys are labeled based on what point they are acting at. So we'll call this point E and this force E. Some of these, you have to figure out the directions based on how they're connected. So if it's a cable, you can't push with a cable. You can only pull with a cable. So this guy is going to be in tension, and that force is also going to be in the same direction as the cable itself. For what's happening down here at the support, so whatever way it cannot move in, there's a force that's keeping it from going through the floor. There's a force keeping it packed in place here. Think through the directions. Think through those equilibrium equations, right? So if I consider what's happening in the x direction here, that tension is pulling to the left, right? So if the tension is pulling to the left, and I have to balance out those x forces, that means that the pin has to act to the right. So these two little guys, if we look at what's happening in the x direction, I can see which way the force on the pin is going to go, just to balance those out. And then for the y direction, the tension is pulling down, force at D and force at E are down. So what does that mean? That the y force has to be on the cable. So if I have down, 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 what does this guy have to be? It has to hold everything up, right? So we'll call this pin C, and the force that is acting on C is a combination of holding everything up, so everything in this y direction as well as what the C. So at the very end, we'll have an addition of both of these guys, and then the overall force at C will be the x squared plus the y squared, and that will give us the force at C. Okay, so that's what this is asking for. if I know D and E, can I figure out what's the tension in the cable? Can I figure out the reaction at C? If I think about the equations that I have to solve for something, as well as the number of unknowns that I have. So what do I not know in this system, and what do I know? So let's say I know the force at D, I know the force at E, and what I'm solving for, I don't know what my tension is, so there's one unknown right here. And I don't know either the x direction or the y direction at C. So there's three things that I do not know in this system. And force balance is not going to be enough to solve for those three unknowns. So this is where I need that third equation. Not just the forces add to zero, but I need to make sure that it's not rotating either. And if I add on these three equations, I can then solve for three pieces of information. Okay, for the moment, I can actually take the moment around any point that I want. So let's walk around a few different scenarios for places that we could take the moment around. And you can make your life easy or really hard depending on where you choose to take your moment around. Okay, so let's say I chose to take the moment around point B. What kind of an equation would that give me? Whatever you take the moment around, you don't have to include the force going through that point. So moment is equal to that. It needs a lever arm and a force, right? So let's say I take the moment around point B. What would that look like? So we could say from B to the force at D, that would be one of them. From B to the force at E, so that would give us a negative clockwise moment. The force at C would not go through this, and we could get Cx. So that's one place that we could take it around. If we took the moment around, maybe we'll take it around point C instead. If I took it around point C, that means I don't have to worry about any of the forces at C. And we would we would split this tension up. Okay, so here's our moment around C. And again, we're coming over to D and over to E. So there's that negative clockwise moment. And to balance that out, we would then need from C up to this tension. So there's a positive moment to counteract it. From this one, we could figure out what the x component of that force is. Okay, so usually when you're walking through these equilibrium problems, the moment is going to be the best place to start because you can get rid of an unknown based on where you take the moment around. And so it will let you solve for something right off the bat, whereas otherwise you might not be able to solve for anything. So start with your moment and then work your way to your force balance. Okay, let me pull open the Excel file for this, and I'm just using this as a calculator. So hopefully that will not be troublesome to you guys. So here is the force at D and E. Here is dimensions of this thing. I can figure out what the angle is here. So let me just draw that in. So this would be the angle right here. given the distance between A and C versus the height here, A to B. So there's that angle. And I'm going to start with a moment, and I'm going to take the moment, in this case, around point C, and that's going to give me what the tension is. So going from C up to B, that distance is right here, this AB. So this is that blue vector going straight up. And if I split my tension into how much of it is pulling over versus down, so the x component is going to be negative and the y component is also going to be negative. Y is opposite, that's going to be the sign, and x is adjacent. So here are, I'm just going to write the equation in because I don't have the magnitude yet. So negative t cosine of that theta. And then we're pulling down t sine theta. There's the y component. So that would be the moment from the tension. And then from these guys, I have a distance of 0.4 in the I direction, or 0.8 in the I direction. And for point D, I'm just going to grab these out of the table itself, so that if I change numbers in the table, it will update my moment calculations. Okay, so zooming in on this guy, in 2 dimensions, the moment is going to be 0 in my I and my j directions. So the only thing left is my k direction. And if I fill that cross product in for one table, I can get that for my other table. So you can see that these negative clockwise moments are going to have to be balanced by that tension. So that means that 0 minus 0.6 is going to be equal to this. So that means this t cosine is going to be equal to this divided by this. So if we have what this guy is equal to now we know what our tension is, right? So our tension is going to be equal to this guy divided by cosine of the angle up here. So I'm just grabbing pieces of information. And here's my x component was negative cosine of that angle. And then my y component is going down, and it was opposite of that angle. Okay, so once I have my tension split into x and y components, and we can make sure here that this times this is equal to 280. We've got our 280 in there. For our D force and our E force, that was something that we were given. So we'll pull those, and they were pushing down on it in the negative y direction. So the last thing we have here is to figure out the force at C, right? So we figured out what this tension was, and then the next piece is to figure out what those other forces were.
So I just need to know when we're thinking on their side, and I'll tell you that for us, it's
Okay, so copying over that free body diagram just so that we can have a good understanding of what's happening here. So we figured out the X and Y components of our tension here. So that's our tension. And we know what D and E were. So this was 200 and this is 250. And what's left is what's happening in the X direction at point C and what's happening in the Y direction at point C. So the Y direction is going to have to hold up all three of those negative forces. So this is going to be negative, and it holds up the 250, the 200, and the 350. So that's what our CY is. Our CY is going to be this 800 to carry all of these guys. It looks like this little one is 350 coming down. Okay, and then in the X direction, it's going to be fighting against the X piece of that tension. So there's the X and Y components of C. And if we want to add those two pieces together, so square root of X squared plus Y squared. So there's the total force for C. And this angle would then be the arctangent of the rise over run. Turn that into degrees. Okay, so that would be the final answer. So what we have here is the reaction at C is X and Y components, and then we also have the tension. And that is what is needed for the Y forces to add to zero, the X forces to add to zero, and also all of our moment forces add to zero as well.